Okay, guys. When we started the day, we started with just balancing these equations and writing the net ionic equation for them. So just copy these down and then take a few minutes. Go ahead and pause the video. Take a few minutes and you can just fill those in. Okay, so if you just pause the video, you should be able to keep seeing these and then just do the total, finish completing the equation, and then write the net ionic equation for all four of these. You need to be able to do this for the test tomorrow. Okay, so pause the video now. Okay, so when we're looking at these and we want to fill these in, then this first one is just a pretty straightforward, just double replacement reaction. So we know that we're going to get lead chromate plus potassium nitrate. Okay, and when we're trying to balance it, we need to know we have to put a 2 there, and now it's balanced. Now the big question is which one is going to be our precipitate? And so when we look at these, think about it. Which one's going to be the solid? Which one's going to be aqueous? And how do you know? I know you're screaming at the camera right now. Potassium nitrate is going to be aqueous because all alkali metals are soluble and all nitrates are soluble. So by process of elimination, without memorization, you know that this is a solid. So we go and do our net ionic equation is going to be Pb2 plus aqueous plus CrO4 aqueous, that's 2 minus, going to PbCrO4 solid. So that's your net ionic equation. That's pretty straightforward. I think you guys are pretty good at that one. Now, this second one, if you look at this compound right here, HC2H3O2, okay, think about what type of compound is that, okay? Since the positive thing is hydrogen, then you know that that's an acid. So this is acetic acid plus silver nitrate. So it's just going to swap, and we're going to get silver acetate plus HNO3. Again, we have to decide which one of these is going to be our solid, which one is going to be aqueous. Okay? So when we're looking at this and you're trying to make that decision, okay? Well, again, all nitrates are soluble. Plus, what type of substance is this? HNO3. HNO3 is an acid. Is it one of our 6 strong acids? Well, hopefully by this point you've memorized that, so the answer is yes. So that's aqueous, and silver acetate then has to be a solid in order for there to be a reaction. Now, when we go and try to do our net ionic equation, you have to realize that since this is acetic acid, is it one of our 6 strong acids? No. It's a weak acid. It means it's a weak electrolyte, which means it's going to stay together. So we write the whole thing together. Now, silver nitrate is still going to be a part. We're going to get Ag plus here, aqueous, but nitrate is going to end up being a spectator ion. And so when we go over here, this is our solid, so this is all together. But since this is a strong acid, this is one of our 6 strong acids, it's going to be a part. So it's going to break up into H plus and NO3 minus. So that NO3 minus is canceling. So we're just left with H plus aqueous. So the key on this one is to know that weak acids stay together. Only strong acids break apart. That's the part that you just need to take from this. That's why I put it up here as an example. Weak acids, weak electrolytes, dissolve as molecules mainly, and so we need to keep it and include it together, not apart. Now, this next one, Li plus water, crud. Let me just move it down just a hair. So Li solid plus water. This is kind of the reaction we saw in the video. When water reacts, remember it reacts as an HOH. So we're going to end up getting LiOH and then hydrogen gas. So then we have to look at, well, will LiOH be aqueous or not? Well, it's an alkali metal. It's also one of our strong bases, so yes, it's going to be aqueous. To balance it, we have to put a 2, a 2, and a 2. Now, the only thing for our net ionic equation here is that we're going to get Li is still going to be a solid. We're still going to just get 2 H2Os. But this time, LiOH, it's an aqueous, strong base, so it's going to be a part. So we're going to get 2 Li pluses, 2 OH minuses, aqueous, aqueous, plus H2 gas. So the only thing that's going to be is that this is not going to be together, it's going to be apart. And since this is a strong base, what's going to happen here? What's going to happen if we put litmus paper in here? What color is it going to turn? That's right, blue. Okay? What's going to happen to the pH? Is it going to go up? Is it going to go down? Well, since it's a base, it's going to go up. Okay? So we're producing a base in water. So the lithium is replacing the hydrogen in water to produce hydrogen gas and an aqueous solution of liquid lithium hydroxide. All alkali metals do this, but really only alkali metals do this one. Okay? So now our fourth one, hopefully we can cram it in here. Our fourth one was sodium carbonate, aqueous, plus, what was the acid that I used? I used nitric acid, I believe. HNO3 aqueous goes to sodium nitrate. And if I didn't use, I can't remember which one I used originally as I erased it, but if whatever acid, it doesn't matter which one it is, okay, that's going to just be broken apart here. Plus, now we're going to make H2CO3. But again, this is a special type. When you use H2CO3, it always breaks down into H2O plus CO2 gas. All right? And then we need to balance it by putting a 2 here and a 2 there. And then that balances it. Now when we go to write our net ionic equation, this is going to be broken apart. Okay? This is going to be broken apart because it's strong acid. This is going to be aqueous, so it's going to be broken apart. So we're really just going to get CO3 2 minus plus 2H plus goes to H2O liquid plus CO2 gas. And what that tells me is that any carbonate plus any acid, this H plus means any acid, doesn't matter what the NO3 minus was. So again, if I used a different acid, it doesn't matter what that is because it's just a spectator anyway. Okay? So any carbonate plus any acid always makes water and CO2. Okay? So we're pretty good on the basic ones, but I wanted to put these 3 in here as show you some of the more rare ones. They're not rare, but the slightly different ones. Weak acid, got to remember, keep them together. When water reacts, it's a reactant. It's going to react as an HOH, not as a hydrogen and an oxygen. And then lastly, when you make carbonic acid, H2CO3, then it's really going to break down into H2O and CO2. So any carbonate plus any acid always makes CO2 and H2O. The other gas-forming reaction that you need to know is that of ammonium hydroxide. So if ammonium hydroxide gets produced, you know that it always breaks up into NH3 plus H2O. And we call NH3, we know that to be ammonia. So that's the other one to look for. If this is a product, just like the H2CO3 would have been a product, if this is a product, then it's not going to make this, it's going to break down immediately into this. So you don't even write this, you just go straight to that. Okay? So you just want to remember those gas-forming reactions. So you are going to have to do your total and net ionic equations tomorrow. Okay? Then we spent another few minutes just talking about what was going to be on the test. Now I gave on the classroom, you have the study guide, so I don't need to spend time going over that. So that's all that's going to be required on the test. So I'm going to move the camera back to the middle. So now, over here, all of this information I'm about to share with you is all going to be bonus. It's all just going to be, it's important for college, it's important for chemistry, but it's not on the AP test, which is why I'm going to make it bonus. There are 4 ways to measure concentration. We already talked about molarity. Molarity is the most common way. You have to know molarity. Okay, so this is not bonus. So everything that you have to be able to calculate molarity of solutions, use molarity in stoichiometry problems, you have to know molarity. However, these 3 other ways you don't really have to know. Now, mole fraction, when we get into gases, you may have to be able to do this one, but for this chapter and being able to convert between the 2, you're not going to have to be able to do the type of problem that we're going to do. But molality is just like molarity, moles of solute. Instead of being liters of solution, though, it's going to be kilograms of solvent. So this time we have to know exactly how much water or how much solvent we're actually adding. Still going to be grams over molar mass divided by kilograms. The third way, and I'm going to do an example of all of these here, 2 examples for you. The other one is mole fraction, which is just going to be moles of solute or moles of solvent, depending upon which one they're asking for. Either one, but not both. Moles of solute or solvent divided by the total moles, which is the sum of both of those. So we have to convert to moles and just divide. There are no units on this one. It's just going to be a decimal. Or mass percent, which is just going to be the part over the whole. What's the mass of the solute divided by the mass of the whole solution? Okay, and it's always times 100 to put it in percent. And so the mass of the whole solution is going to be the mass of the solute plus the mass of the solvent. These 2 here. Okay? So if we're trying to figure out how to do this, okay, we can convert. The goal is going to be, if I'm given one information, how can I convert it into all of them? So there are 2 examples that I want to do, and then we're just going to call it a day. And again, there's just going to be a problem like this on the test that you can use then. So in the white book here, page 567, if you look at that and look at question number 41. Question number 41 on page 567. I'm going to move it back over this way so you get a better head-on shot to it. Okay, so page 567, number 41, says that we have 571.6 grams of H2SO4 per 1 liter of solution, and we're also given that the density of the solution is equal to 1.329 grams per cubic centimeter. Okay? So that's my given information. That's given in the problem. Then it goes through and says, okay, well, we want to go and calculate. Let me get the right order here. So we want to calculate, okay, the first thing is calculate the mass percent, then the mole fraction, the molality, and the molarity. So the first thing we're going to do is the mass percent. So I want to come up here, mass percent. Well, I have the formula right over here, but mass percent is equal to the mass, in this case, of H2SO4 over the mass of the solution. times 100. So, given this information, do I know the mass of the H2SO4? Well, yeah, it's given to me right here, 571.6 grams. So I know it's 571.6 grams of H2SO4. But now I need the mass of the solution. Well, the given tells me that I have 1 liter of the solution. Okay? I also know the density is 1.329 grams per cubic centimeter. So, the mass of the solution is going to equal 1 liter, you should know this, is how many milliliters? 1,000. A milliliter is the same as a cubic centimeter, so it's going to be 1,000 cubic centimeters times 1.329 grams per cubic centimeter. So the mass of the solution is 1329 grams. So I can just plug that into here, 1329 grams of solution times 100, and this turns out to equal 43.01, I believe, is the answer. 571.6 divided by 1329, 43.0101% H2SO4. Okay? So that's mass percent. Now the key on this is that know that a lot of times when it says that 571.6 grams per liter, we forget about the per liter. It doesn't always stand out. But they gave you the volume here that's per liter. Molarity also is going to be so many moles per liter. So you got to know that that's per 1 liter. Okay? Now B wants the mole fraction. Well, that's going to be moles of H2SO4 over total moles. So, well, I have 571.6 grams of H2SO4. I can convert that to moles using the molar mass. 1 mole over 98.1 grams. That's the molar mass of H2SO4. So that turns out to equal 571.6 divided by 98.1. That's going to equal 5.83 moles of H2SO4. But now I need moles of solvent, moles of water. Well, this is not grams of water. This is grams of solution right here. So I need to figure out, well, of this 1329, how much is water? Well, we know 571.6 grams is H2SO4. So the mass of the water is equal to 1329 grams of solution minus 571.6 grams of H2SO4 solute, and that's going to give me 1329 minus 571.6 equals, it's going to give me 757.4 grams of water. Well, to get the mole fraction of that, I have to then go and get moles. So 757.4 grams H2SO4. We should memorize the molar mass now to be 18.02 grams. So divided by 18.02 gives me 42.03 moles of water. So now my mole fraction, X, of H2SO4 is going to equal moles of H2SO4, which is 5.83 moles, H2SO4, divided by total moles, which is 5.83 moles, plus the moles of the water, 42.03. Okay? So we're just going to put that in over here, 42.03 moles. So our mole fraction of H2SO4 is equal to 5.83 divided by parentheses 5.83 plus 42.03, close the parentheses, equals 0.122. And there are no units on that because moles all cancel out. So the mole fraction of our solution is 0.122. Okay? That's how many moles of H2SO4 over total moles. Okay? So that's the first two. We calculated the mass percent. We calculated the mole fraction. Now we're supposed to calculate the molality and the molarity. Okay? The molality and the molarity. So we have all this down. Make sure we have it. I'll get out your way. See if it over here gets a better shot. Oh, keeps wanting to move. How about if I do this? That's too much. No, doesn't want to give me a good shot over here. All right. Hopefully, I'll just stand still and then you can read it. Okay. Sure looks like it's all backwards. All right, so I can't pause this. It sure looks like the writing is showing up backwards on the board, mirror imaged. Maybe that's just the way I'm looking at it. Okay. If not, hopefully you're listening and copying down and figuring it out. This is the best I can do. So now we need the molality and the molarity. Oh. Density is equal to 1.329 grams per cubic centimeter. So, to get C, the molality, which is always little m, it's equal to moles of solute divided by kilograms of solvent. Well, I just erased it, but we know the moles of solute to be 5.83 moles. And we had 750, what did we have? We had 1329 minus 571.6. We have 757.4, so 0.7574 kilograms of water. That's going to be my molality, so 5.83 divided by second function answer, and you end up getting the wrong answer. 5.83 divided by 0.7574 equals 7.70 molal. So that's the molality. Because we already knew this, we just got to make sure you put kilograms of water. But we had already calculated that in the previous part. And then lastly, D is the easiest one, molarity. Okay, that's capital M. It's equal to moles of solute over liters of solution. Well, we know the moles of solute is 5.83 moles H2SO4, and we were told that it's in 1 liter, so it's simply going to be 5.83 molar. So it's a very simple, straightforward problem. Okay? So once you get the first two, once you get the mass all taken care of, then the rest is really pretty easy. Okay? So, all we need to be able to do is we should be able to calculate these. Now the good news is on these two is that all those equations are going to be given to you. You don't have to memorize the equations. They're all given to you. So that's all good. So now if we go and we look at one more example. Example 2. A 1.37 molar solution of HNO3 has a density of 1.10 grams per cubic centimeter. What is the molality, mole fraction, and mass percent of this solution? Okay, so in other words, we just got to convert from molarity to these other three. So, we take our given, we have to understand that what this means is that we have 1.37 moles, it's not supposed to be HNO3, sorry, it's supposed to be H3C6H5O7, which is citric acid. Okay, that's the one I did. So all the other information is right. It's just citric acid. It's not going to change much except the molar mass here. So it's H3C6H5O7. So we have 1.37 moles of C6. Let's try that again. H3C6H5O7. And we know that the density, and that's moles over 1 liter, and that the density is equal to 1.10 grams per cubic centimeter. So again, it doesn't matter if we want to do this kind of in the same way we did the mass percent. Doesn't matter which order we find these. Mass percent, mass of H3C6H5O7 divided by the mass of the solution. Well, to get the mass of the C6, the mass of the H3C6H5O7 is equal to 1.37 moles times the molar mass of this. So the molar mass of this is 12 times 6 is 72, plus 8 hydrogens makes 80. 16 times 7 is 112, so 112 and 80 is equal to 192. Okay, so that's going to give me 1.37 times 192 is equal to 263 grams. Okay, now again we can take the mass of the solution. The mass of the solution is going to be 1 liter, which is 1,000 cubic centimeters times this, so we're just going to move the decimal 3 places, so it's going to be 1,100 grams there. So the mass percent is going to equal 263 grams of H3C6H5O7 divided by 1,100 grams of solution times 100, this is always times 100, is equal to, divided by 1,100, is equal to 23.9% H3C6H5O7. So there's your mass percent. Now, to get the mole fraction, we're going to have to do the same thing. Now, we already have moles of this, so we just need moles of water. Well, how do we find out how much water we have? Think about it. How did we do that last time? How do we get the amount of water? Well, we know the whole solution is 1,100 grams. We know that 263 of those are the solute. So the other part is the solvent. So the mass of the H2O is equal to 1,100 grams of solution minus 263 grams of the H3C6H5O7. So that's going to give me 837 grams of water. Okay? So to get the moles of water, I'm going to go 1 mole divided by 18.02 grams. And that's going to give me 837 divided by 18.02 is equal to 46.4 moles of water. So my mole fraction, X, of the H3C6H5O7 is equal to the moles, which is given as 1.37, divided by 1.37 plus 46.4. So X is equal to 1.37 divided by parentheses 1.37 plus 46.4 equals 0.0287. And again, there are no units on that because moles cancel out. Okay? So that's my mole fraction. So that's the mole fraction B. So now to find your molality, the molality is simply moles over kilograms. Okay? So we know moles here. We already know grams of water right here. So it's simply going to be 1.37 divided by kilograms, 0.837. So for D up here, I know this is kind of messy, but the molality is going to equal 1.37 moles divided by the 0.837 kilograms. So the molality is equal to 1.37 divided by 0.837 equals 1.64 little m molal. So, actually this is not D, this is just C. Okay? So the mass percent, 23.9. The mole fraction, 0.0287. And the molality is 1.64. Okay? So, these type of problems are going to be totally bonus, but it's converting between all the different ways of measuring concentration. So, if you remember how to do it again, the equations are going to be given. So the key on all of this is you have to have the density in order to be able to convert between grams, the volume of the solution, liters, and the grams of the solution to get your mass here. Density is the key, so that has to be a given. There's no way to do that without. Okay? So basically that's what we did in class today, kind of work through this. It took a little longer because I gave them time to kind of work on it and look at it, but hopefully this will give you a chance. There are some other practice problems that maybe I can give to you to work on in this first period. Okay? Hope you like this. If you do, subscribe to the channel. Thank you.